Welcome to Advanced Group Theory. Today, we are going to explore one of the most beautiful and powerful counting principles in mathematics, the class equation. Imagine trying to understand a massive, complex structure by breaking it down into perfectly manageable, non-overlapping pieces. That is exactly what we will learn to do today. Let us dive in. To begin our journey, let us think of a group like a large high school. In this school, students form distinct social cliques or friend circles. In group theory, we call these cliques conjugacy classes. Elements in the same conjugacy class behave in a fundamentally similar way. By grouping elements that interact similarly, we can start to break down the total order of the group, which is simply the total number of elements it contains, into smaller, distinct parts. This makes analyzing the entire group much easier. Now that we understand conjugacy classes, let us look at a very special subset of our group. In our high school analogy, some students are incredibly popular and get along with absolutely everyone. They do not need a specific clique to fit in. In mathematics, these universally friendly elements form what we call the center of the group. Because an element in the center commutes with every single element in the group, its conjugacy class contains only itself. This means its class size is exactly 1. This brings us to the formal mathematical definition of the center. The center, denoted by Z of G, is the set of all elements X in the group G such that X times G equals G times X for every element G in the group. Conceptually, this just means we are collecting all the elements that can be swapped in order without changing the result. If a group is highly symmetric, this center might be very small, but it is always our starting point for counting. When the number of commuting elements increases, the center grows. But what about the elements that are not in the center? For any element X that only hangs out with a specific clique, we look at its centralizer. The centralizer is the subgroup of elements that commute specifically with that one element X rather than with the whole group. By understanding how many elements commute with X, we can figure out exactly how large its specific conjugacy class or clique is. This is a crucial step in mapping out the group's entire structure. Let us see how we calculate that class size mathematically. The size of the conjugacy class containing X is given by the index of the centralizer in the whole group. We write this as the total group size, order of G, divided by the size of the centralizer of X. Physically, as the number of elements that commute with X decreases, the size of its conjugacy class increases. This formula perfectly links a subgroup size to the size of a behavioral clique, allowing us to count efficiently. With these pieces in hand, we are ready to build our main equation. Because conjugacy classes perfectly divide the group into non-overlapping subsets, the total number of elements in the group must equal the sum of the sizes of all these distinct classes. We simply separate the classes of size 1, which collectively make up the center, from the remaining classes that have a size strictly greater than 1. This logical separation is the core idea behind our counting method. This logical separation gives us the famous class equation. The total order of the group, G, equals the size of the center, Z of G, plus the sum of the sizes of all the remaining larger conjugacy classes. The summation symbol adds up the indices of the centralizers for representative elements X sub I. As the group becomes more complex and less commutative, the center shrinks, and the summation part grows to account for the rest of the elements. Every single element is perfectly accounted for without any double counting. To make this abstract formula concrete, let us look at this diagram. The entire large circle represents the whole group G. Notice how it is perfectly sliced into non-overlapping regions. The inner circle is the center, containing individual dots representing conjugacy classes of size 1. The outer wedges are the larger conjugacy classes, like class of x1 and class of x2. No element is left behind and no element is counted twice. This visual perfectly captures what the equation does. Now that we have our formula and visual intuition, let us apply it to a concrete example, the symmetric group S3. This group consists of all possible rearrangements of 3 items. First, we note the total order of the group is 6. Next, we find the center. In S3, the only element that commutes with every other element is the identity element, which means doing nothing to the items. So, the center has a size of exactly 1. We will use this to start our equation. Continuing with S3, we have 5 elements left to categorize. These remaining elements divide into 2 distinct conjugacy classes based on how they rearrange items. One class contains the 3 elements that swap exactly 2 items. We will call it size 3. The other class contains the 2 elements that cycle all 3 items in a loop. This gives us a second class of size 2. We have now identified all the pieces we need to construct our final equation. Let us put it all together for S3. We substitute the size of the center, which is 1, and the sizes of our 2 larger classes, which are 3 and 2, into the class equation. Adding them up, 1 plus 3 plus 2 equals 6, which perfectly matches our total group order. This confirms that our counting method is correct, translating the abstract structure of permutations into simple addition. The physical meaning is that all rearrangements are fully accounted for. Before we move on, let us see this with another important example, the quaternion group Q8. This group is often used in physics to represent 3-dimensional rotations. It has exactly 8 elements: 1, minus 1, I, minus I, j, minus j, k, and minus k. In this specific group, only the elements 1 and minus 1 commute with everything. Therefore, they form our center. We will start our counting process by noting that the size of the center is exactly 2. Continuing with our quaternion group, we know the size of the center is 2. We have 6 elements remaining. These elements pair up naturally into 3 distinct conjugacy classes. The class containing I and minus I has exactly 2 elements. By symmetry, the class for j and minus j and the class for k and minus k also contain exactly 2 elements each. We now have 3 separate groups, each containing a pair. This sets us up perfectly for the final calculation. Finally, we substitute these values into the class equation for Q8. The total order of 8 equals the center size of 2 plus the 3 separate classes, each of size 2. 2 plus 2 plus 2 plus 2 equals 8. This perfectly illustrates how the class equation partitions a highly structured rotational group. Every single element is accounted for exactly once, reducing complex symmetries to basic arithmetic. The final answer shows the structural blueprint of these 3-dimensional rotations. We have covered a lot of ground today. To summarize, the class equation is a powerful counting principle that expresses the total number of elements in a finite group as the sum of the sizes of its conjugacy classes. It elegantly separates the universally commuting center from the rest of the group. By turning abstract algebra into simple addition, it unlocks the ability to prove deep theorems and classify symmetries in physics and chemistry. Great job following along.